No, no, no. Great. Maybe. It's not letting me switch screens for some reason. Oh, for heaven's sake. Should not be this hard. Why will you not let me? Alright, let me switch back over here. Sorry. It's being a pain. Alright, so when I go back over here to these vectors, what did that have? It had 1, 0, 1/2, 0 when we row reduced, and then 0, 1, negative 3/2, 0. I think that was what the row reduction looked like.
Yeah.
Yep. Okay. So remember, this is our free variable, so this can be anything. So if I make that constant, say, 2 to get rid of my fractions, so if I say C3 is 2, then C2 would have to be 3, and C1 would have to be negative 1. Again, I'm just plugging in. Remember, we can plug anything we want in for that free variable. So if I chose a 2, so we get rid of those constants, or excuse me, get rid of the denominators in the fraction, and then just solve for the other 2. So what that tells me is that if I go back up to the original here, that would tell me that if I use negative the first one plus 3 times the second one, and then plus 2 times the third one, which was 5, negative 3, negative 7, 2, I should get zeros everywhere. And you can check the arithmetic and make sure that it works. This would be negative 1 minus 9 plus 10 gives you 0. And 3 plus 3 is 6, minus 6 is 0. And you can check the other 2 entries as well. So we really do have a linear combination of the original matrices that gives us the 0 vector without using zeros to start with. So that's the idea here. All right. Now, one of the things that I talked about before break was that we're treating different things as vectors, right? We treat matrices as vectors, we can treat polynomials as vectors, we can treat regular old vectors as vectors, but everything's boiling down to putting it into a matrix and row reducing the matrix and seeing what happens. So when we put, notice in this case, when we put this into a matrix, we can look at the particular entries in the matrix and write them down in a column. So notice that I had the 1, negative 3, 4, 1 here in this first matrix. I can just write it down the first column. And then if I do the same order, notice I went 1, negative 3, 4, 1. I want to make sure that I do -3, 1, 6, -1 for the second one, and then 5, -3, -7, 2 for the third one. Now, the order of the first one doesn't matter how you put it in the first column, because just like what I'm saying here is it wouldn't matter which order we had the equations in, but once you pick an order for that first column, you got to follow the same order for the other columns, making sure everything matches up. Because again, we're trying to match entries, right? This was an upper left entry, this was an upper left entry, this was an upper left entry. So what I'm saying is that the actual individual orders of the rows don't matter, but you got to make sure you have columns corresponding to the right places. Does that make sense? Okay. Are we okay with that? Any questions about this particular problem?
So does that mean that it's not linearly independent?
That's exactly right. It means it's not linearly independent because we did not get a unique solution to the homogeneous system. We didn't just get the trivial solution. We got infinitely many. Is that okay? All right. So I think I mentioned this before break as well, is why do we care about linear independence? And the whole point of this is that, going back up to the previous example here, we said that we could use zeros to get the zero vector, or we just saw that we could use -1, 3, 2 to get the zero vector, or there are other combinations that we could use to get the zero vector. So there's not just one way to write the zero vector, there's a whole bunch of ways to write the zero vector. However, if you have a linearly independent set, what you have is that if S is, I'll say, V1, V2, not to Vn, is linearly independent, and if, I'll call it W, is in the span of S. Remember, span is the set of all possible linear combinations that you can make with the vectors in the set. Okay, so if S is linearly independent and W is in the span, then there is only one way to write W as a linear combination of the V1 out to Vn. All right. So linear independence means that if you can write it as a linear combination, if you can write a vector as a linear combination, that's the only way you can write it as a linear combination. There's not two different ways to do it. In that previous example that we did, there was more than one way to write a linear combination that gives you a zero vector, and in general that would mean that anything that was in the span of those vectors would have multiple representations through a linear combination. So if we have a linearly independent set, though, there's only one way to do it. So what that tells us later on is that we can start talking about coordinates, if you will. You've talked about coordinates pretty much ever since you learned about graphing, right? So as soon as you started learning about how to graph things, you've talked about coordinates of points in particular. Well, the whole idea of coordinates is that those coordinates are representations of how far in the x direction do you go? How far in the y direction do you go? And so on down the line. The idea behind that is that if I say that they had the point 3, 4, I know that I had 3 units to the right and 4 units up, which means I had 3 copies of the vector that would be 1, 0, and I had 4 copies of the vector that would be 0, 4. And added together, that would give me the coordinates 3, 4. And I know that there's only one set of coordinates that give me that point. So that's the importance of linear independence, is that if I have a way to write it as a linear combination, that's the only way that I can write it as a linear combination, period. Okay, and so that's going to lead us into being able to do things like talking about coordinates relative to what we refer to as a basis, and that's what's in the next section. All right, so that's the importance of linear independence, at least for our purposes. All right, so let's talk about a few theorems that go along with linear independence. So the first one says that any set that contains the zero vector has to be linearly dependent. Well, let's think about why that has to be the case. Remember that our definition for linear independence, let me scroll back up here again. Our definition for linear independence said that if I have a linear combination that gives me the zero vector, then all of those constants have to be zeros. Well, let's go back up to this theorem here. So let's say you had S was the set V1, V2, up to some Vn, but I stuck 0 in there as well. Okay. Can you give me a linear combination of these vectors? So a V1, I'm going to fill in the blanks for constants here. A V2, a Vn, and then with the 0 vector and 0. Can you give me values for these constants? Can you fill in the blanks so that I don't have all zeros here, but I do get the 0 vector on the right-hand side? What do we think? What do you think we could use for numbers in here? Certainly, if I put all zeros in here, it'll work, right? Okay. But what else could I use besides all zeros? It's okay if some of them are zeros. They just can't all be 0. Any ideas? Maybe my audio is not working. All right. Well, anyway, let me go ahead and just talk then. All right. So if we could notice that over here, we can use anything that we would like, right? So say I can even use a 1 here. What the 1 times the 0 vector is still the 0 vector. So then I could use zeros everywhere else and get what I need, right? So this is not using all zeros as my constants. I can use zeros for all of these and 1 here and still get the 0 vector. So I don't have that all of the constants had to be 0 to give me the 0 vector. So that's why this one is linearly dependent. All right, let's look at the next one. I have no idea if I'm having trouble with my audio or not because I hear things in the background, but I'm not. It sounds more like airplanes are going by than anything else. Anyway, we have the second one here. Let's say we have a set with at least 2 vectors. Then we have a linearly dependent set if and only if at least one of the vectors is expressible as a linear combination of the others. So one of the reasons why I wanted to go through this particular one is that it wanted to remind you of the idea of an if and only if statement. Remember, for if and only if, we have to go both directions. We have to prove if it's linearly dependent, then one of the vectors is expressible as a linear combination of the others. That's the left to right direction. But then we also have to say that if at least one of the vectors is expressible as a linear combination of the others, then it's linearly dependent. So let's suppose, just go through this real quick. Let's suppose that S is linearly dependent. So remember, linear independence says that a linear combination that gives you the 0 vector must have had all zeros for the constants. So linearly dependent means that there exists constants C1, C2. Just assume that my S here is V1 out to Vn like I had up above. Then there exists constant C1 out to Cn such that our C1 V1 plus C2 V2. Oops, I should have said not all zero to start with. I'll write that down here in a second. And not all the C sub i's are equal to 0. We have at least some of these constants that are not 0. They don't all, some of them could be 0, but linearly dependent means that we would have a linear combination that gives us the 0 vector where at least one of these is not 0, like what we had up here in the previous part. At least one of these vectors was not 0. Or excuse me, at least one of the constants was not 0. Okay? All right. So, if they're not all 0, let's suppose for argument's sake that C1 was not 0. And we actually have a word for that in mathematics. We say, without loss of generality, let's assume that C1 is not 0. Let me talk about just this again. Part of the point of linear algebra is an introduction to proof course. Let me talk about this for just a second about what I mean by this statement. So remember in mathematics, when you're trying to prove something, you got to prove it in the general case. A specific example doesn't work if you're trying to make a general proof of a general theorem. Okay? So when I make statements like this, I have to be very careful that I really don't lose generality. So what I mean by this is that notice that we just picked, when I wrote V1, V2 out to Vn, I picked some arbitrary order of the V's. I didn't really care what the order was. We know when you write things as set notation, you don't really care what the order is. Now I do know, by supposition here, I do know that not all of these are 0. So if I choose at least one of them that's not 0 and just make it the first one, I haven't changed anything. So I can just reorder my V's, renumber them if you will, and just make sure that the first one is the one that has the non-zero constant. So that's all that this statement means here. It just helps me with notation that I don't have to say CI, VI, or have weird notation. I can just say that, okay, the order here didn't really matter, so I'm just going to assume it's the first one. Okay? I could have just as easily assumed it was the last one if I wanted to. Right? That's all the without loss of generality part means. Okay, I want to show that one of the vectors is a linear combination of the others, so I'm going to show that V1 actually is a linear combination of the other ones. The whole reason why I needed to assume that this particular constant was not 0 is because I want to get this V1 all by itself if I'm going to show that the vector is expressible as a linear combination of the other ones. To get this one by itself, I've got to divide by C1, and I can't divide by C1 if it's 0. So just to finish this off then, I'll say then we have that V1 is equal to, well, let's just think about what happens when we move it to the other side. Negative C2 over C1 V2. It'll be a minus C3 over C1 V3. Minus, minus, minus Cn over C1 Vn. So thus, V1 is a linear combination of the other vectors, the V1, V2 out to Vn. Questions on that? Is that okay? Does it make sense? It's hard to get feedback over microphones. All right. Is it okay?
Yeah.
Yeah? All right. Cool. All right, so we still need to go the other way. So I'm going to, because I didn't leave myself enough room to write the rest of it, I'm going to actually erase this now. But does anybody need more time to write it down? All right, so I'm going to erase it just so that I have room. All right, so I still need to go the other direction. Oops. I actually need to use a pen to write, though. All right, so the other direction is that we're going to assume, we'll suppose. I like to use the word assume when I'm doing proof by contradiction. So we're going to suppose that one of the vectors is a linear combination of the others. Let's say, again, without loss of generality, let's say we have that V1 is equal to C2V2 plus C3V3 out to CNVN. And again, here, what I mean by the without loss of generality statement is that I know one of them is a linear combination of the others, so I might as well just say it's the first one, just by reordering the vectors in the set, since the order doesn't matter of the elements in the set. That's all I mean by that statement. Now, again, to show that it's linearly dependent, I know that I need to get 0 vector on the other side. So what I'm going to do is just subtract the V1 to the other side. And I'm going to be a little bit pedantic about it, not just write negative V1. I'm going to write negative 1 times V1 plus C2 V2 plus CNVN. Now, the reason why I specifically wrote out the negative 1 is because, remember, to show linearly dependent, I need to make sure that I have constants not all 0 that give me the 0 vector. Here's my at least one of the constants that's not equal to 0, right? I don't necessarily know that the C2, the C3, and the Cn aren't 0. They could be, all right? I don't know which of these would be non-zero at all. However, I know for a fact that this one is not 0. Because certainly not today, negative 1 is not equal to 0. Now, when you get to abstract algebra next semester, you might, if you're taking abstract algebra, you might have a situation where negative 1 really is equal to 0. You never know. Okay, but today, these are real numbers. You don't have to worry about that. Negative 1 is not equal to 0. So, therefore, S is linearly dependent. Questions on that at all? All right, let's compare statement B to statement C here. So statement B said that if S is a set with at least 2 vectors, it's linearly dependent if one of them is expressible as a linear combination of the others. C is just basically the negation of both statements, isn't it? A set is either linearly dependent or it's linearly independent. This says at least one of the vectors is expressible as a linear combination. This one says no vector is expressible as a linear combination. So C really is just, well, if you remember, if you've had discrete, if you remember things about contrapositive, if you had this if it's linearly dependent, then at least one of them is a linear combination of the others. The contrapositive would say that if none of them is expressible as a linear combination of the others, then it's linearly independent, right? And we know from logic purposes that contrapositives are logically equivalent to the original statement. So really all this statement C is just a combination of the two contrapositives of this statement up here. So C is just the same statement as B, just written in the as a contrapositive of the if and only if you will. All right, so that's why C has to be true, is because we already showed that B had to be true. Now let's think about D along the same lines here. Instead of having at least two vectors, we have exactly two vectors. So it says S is linearly independent if and only if neither vector is a scalar multiple of the other. But let's think about it in terms of being linearly dependent. If it only has two vectors and is linearly dependent, what has to happen if one of them is going to be a linear combination of the other? Of the others, I should say, but I said it. If you only have two vectors, V1 and V2, if it's linearly dependent, how is one vector going to be a linear combination of the other vector? What does it have to be? It has to be a constant times it, right? That's from part B, isn't it? Okay. So if it's going to be linearly dependent, one vector has to be a linear combination of the others. Well, the others is just other. So that means that one has to be a constant times the other for linearly dependent. So if it's going to be linearly independent, this can't happen. It's not a scalar multiple of the other. So what that means is that by example here, if let's say we had the set, let's say S is, let's say 2 plus x minus x squared and negative 6 plus 3x minus 3x squared. And this is in P2. What do you notice about the first polynomial with relation to the second? Oh, no, sorry. I should have changed these signs, shouldn't I? Let me change this to a minus. Maybe I'll change it to a minus. What, a minus and a plus? That'll be better. Now what do we notice about those two? If we look at the first one here, what do I need to multiply the first one by to get the second one?
Negative 3.
Negative 3, good. So negative 6 minus 3x plus 3x squared is negative 3 times the 2 plus x minus x squared. So what does that tell us about S? It tells us it's linearly dependent. Good. Does that make sense? We okay with that? All right. Cool. All right. So let's go down to this theorem here. Now, one thing I want to notice about what the theorem says is notice that in this case it says we've got this subscript on the k is bigger than this exponent, if you will. It's not really an exponent. It's telling you basically how many coordinates you have. That exponent, if you will, on the r. If that k is bigger than that n, then it says that the set has to be linearly dependent. So let's think about, before we even try to write down a proof here, and the proof's going to go back to our systems linear equation stuff. But before we try to write down a proof here, let's just think about why this must be the case. If we think about something that's in Rn, to get coordinates, I just need n spots for coordinates, right? And I mentioned before that one of the reasons why we care about linearly independent is that we can start thinking about coordinates. Well, this gives you more information that you could possibly need for coordinates, right? I don't need, say if I had R3, I wouldn't need 5 vectors to tell me where something is in R3. Because you'd already know in R3 you only need an x direction, a y direction, and a z direction. That's all you need for R3, right? So if I had 5 vectors in here, I know that would be too many. So I wouldn't be able to have coordinates relative to that particular set. So it shouldn't be a huge surprise that if I have too much information, it's going to be linearly dependent as far as that goes. All right, so let's see why this is the case. If you've got vectors in Rn, let's see how you would, let's set up a system of equations. So let's say we had V1, just for argument's sake, is, I'll say A11, A212, A13, onto A1n, V2, using the same numbering scheme here. I know, lots of notation here, but all I'm using for the subscripts is that the first subscript is referring to the number vector that I'm on, and then the second one is just which coordinate am I in for Rn. All right, so we want the C1 V1 plus C2 V2 plus CK VK to be equal to the zero vector, which we know in Rn is just a bunch of zeros. This is what we have to try to consider anytime that we're doing linearly independent or linearly dependent, right? We have to start with a linear combination that gives me the zero vector. What we need to show in this case is that this has solutions that don't involve, or excuse me, that solutions other than just using all zeros for the constants. So what we're going to do here is just set up a system of equations. So this C1 is going to get multiplied through by on the V1. This C2 is going to get multiplied through on the V2. And so on down with the CK is going to get multiplied through on the VK. And then we're going to equate components. So the first one's going to be A11C1. That'll be your first component. You'll have an A21C2. That'll be your second component. And then you'll have an AK1 CK. That has to equal 0. So this is just equating first components. And then for second components, you would have A12C1, A22C2, AK2CK is equal to 0. And keep going until you get to the last component. So you would have A1NC1, A2NC2, AKNCK is equal to 0. Okay, so now let's look at the number of equations versus the number of unknowns. How many equations do we have here? How many total equations do we have? 10 of them. And the unknowns are the C's. And how many unknowns do we have? Okay, good. So, if we have n unknown, well, we have k unknowns and n equations. Do we have enough equations to balance out the unknowns to get a unique solution here?
No.
No, good. Or we have more unknowns than we have equations. We know that this system has infinitely many solutions. right? Think about what the matrix would look like in your reduced row echelon form, right? If you've got this, would have more columns than it has rows, so you can't possibly get a pivot in every column, which means that you can't possibly get a unique solution. So that tells us that S is linearly dependent. All right, so just to illustrate what we're talking about with these last few things, let's look at these examples and then we'll call it a day here real quick, all right? So let's look at this first example. Why is S linearly, well, let me just ask that it's not why is. Looking at this particular set, is it linearly dependent or linearly independent? Looking at the first one.
Dependent.
Because?
There's just a whole thing of zeros.
Good, right. So this one's linearly independent, or excuse me, linearly dependent because we've got the zero vector as an S, right? 0, 0, 0 is the zero vector in R3. So that one's linearly dependent because the zero vector is in there. Remember, if the zero vector is in the set, it's automatically linearly dependent. The next example is actually problem 1b on page 248 of your text. What do you say about this particular set? Is it going to be linearly independent or linearly dependent, just by looking at it? This goes back to the last theorem. How many components does each vector have? 2. 2. Good. And how many vectors are in my set?
3.
3. So what does that tell you?
Linearly dependent.
Good. This one tells you it's linearly dependent by the previous theorem, right? It's a set of 3 vectors in R2. And then the last one looks a lot like the example that I did before. This one is linearly dependent because why? What do I need to multiply the first one by to get the second one?
2.
2. Good. So the 6 minus 4x plus 2x squared is equal to 2 times the 3 minus 2x plus x squared. All right. So this last one here, I'm not going to do it right now just because of time, but this last one here is asking if this is a linearly dependent set in R3 or not. So, or excuse me, what values make it a linearly dependent set? Let me just talk real quick about how you would do that. So remember we talked about putting the vectors as columns. Now, I didn't write it as a matrix. Notice I wrote it as a determinant. Remember, to show that it's linearly independent, we would need a pivot in every column. Well, if I get a pivot in every column, it also gives me a pivot in every row, which means it's row equivalent to the identity matrix. When I row reduce, I would get the identity matrix, which would mean that the matrix is invertible. Right? Remember that list of stuff we have going about whether or not a matrix is invertible? Okay. So remember, for determinant, you can check whether or not a matrix is invertible by checking whether or not the determinant is 0. So in this case, I would set the determinant equal to 0 and find the values of lambda that give me this. So that gives me a linearly dependent set. All right. So what I will do is finish off these problems as a recording, and I'll post it on YouTube as well. I'll do that later this afternoon, so you can go back and look at those. And then the last example is the other video that I asked you to watch today about the Wronskian. So give that last one a try. See if you can do that one based on the video I asked you to watch today. And then I will do a video to do these last 2 examples to go through those for you. Sound like a plan?
Yeah.
All right. I will be on Zoom tomorrow. I'll say maybe at 11 o'clock. I'll be on there from 11 to noon. So if you've got questions, or if you want to make an individual appointment with me to talk, we can do that too. I'm happy to do that. I'm more than happy to answer questions. I know you got homework that's due on Friday. To be able to ask me questions about that would be important as well. So just give me a holler. Like I said, I'll be on Zoom tomorrow at 11 for office hours. And then if you got questions, you can always feel free to ask me then or set up a different time. I would also ask you to send me an email about how you thought this went today. All right. So anyway, I will talk to you all later. Hopefully this worked out okay, but if it didn't, please let me know. Just send me an email. You're not going to offend me if you thought it sucked. So please let me know how it went. All right. I'll talk to you all later.